Okay guys, in this video lesson we're going to start taking this idea of charge and then moving into this idea of how do we get it to move now. Okay, we are in the static side of this, so we're still not going to have it flowing through wires and that kind of stuff, but we do want to be able to transfer it from one thing to the other because we do get these charge imbalances. All right, so with movement of charge, the first thing we want to talk about is this idea that we have to conserve it. All right, just like conservation of energy, just like conservation of mass, when we have electrical charge, the total charge in our universe is always going to be constant. Okay, which means if we have to lose, X amount of charge from one object, that means some other object has to gain that exact same amount of charge. Keeping that in mind, we then can start to look at how much is lost and how much is gained by different substances and what forces are in play to cause that. Okay. Now, as we look at objects becoming charged and moving from place to place, we have this imbalance that happens. And there's two different ways that we can look at it. First of all, through the idea of electrons. Okay, so electrons, they're able to move in solid substances. Okay, in particular, they're able to move on the surface of solid substances. Okay, now most notably for that, and the one that we want to focus on are metals, because metals are considered to be conductors, and they do a really good job of allowing electrons to move through them. Okay. We also have things called ions. Okay, so electrons are individual subatomic particles. Ions are complete atoms. Okay, so if you remember, let's take something, for example, like the sodium atom. Sodium has 11 protons in it. Sodium has 11 electrons in it. Normal conditions, sodium is neutral. Okay, 11 protons, 11 electrons. However, if we were to strip one electron away from sodium, that means it now would have 11 protons and only 10 electrons. In that case, it now becomes an ion. It has lost an electron. The same thing would happen if we gained an electron to an atom. Okay, in those cases, we now have an entire atom that is charged. It's different than just having a single electron that has a charge to it. This is an atom with protons, neutrons, electrons in it that has an imbalance within itself. These ions, they are able to move freely through other phases of matter, and in particular, liquids. Okay. Nothing really travels really well in terms of charge through air. Okay, air acts as a really good insulator, to be honest. So you might want to jot down the word liquids here, because ions, once you dissolve them into water, are able to move very freely, and we can conduct current or flow of current through water using these ions. But in metals or solids, that same type of conduction is going to happen by electrons at a time, not ions. Okay. Now, when you have movement of electrons, one of the first things that we want to talk about is the buildup of these extra electrons on things, and what can one of those results of that. Okay, that one result is static electricity. Okay, there's lots of other results too, but one we're going to focus on now is static electricity. Now, I don't know about you, but in the wintertime, I get shocked a lot. Okay, I wander across my house. I have carpet on my floors. I reach out to grab a door handle. I touch the door handle, and right before, not after, not when, but the instant before I touch that handle, I get a little shock. Okay, it's like, where did the electricity come from? Okay, I'm not touching an outlet. I don't have, a battery in my hands. Where's it coming from? That's called static electricity. And static electricity comes from friction. Okay, what happens is, as you move through the world, if you drag your feet on your carpet, or if you're drying your hair with a towel, you're increasing the friction between these different particles. In the world of chemistry, we talk a lot about electrons being chemically transferred from one thing to the other. In the world of physics, that can happen physically also. We can literally physically strip electrons off of one substance and put them onto something else. Okay? When that happens through friction, we call that a redistribution. When that happens with friction, it redistributes the charge. Okay? Creates it, makes it unbalanced. Now, that happens all the time. Okay, walking around the room, that kind of stuff, getting in and out of vehicles, you have this charge imbalance. Most of the time, it's not a big deal. But if you build up enough of this charge imbalance, and then you touch something that does not have this or is neutral, it can discharge. Okay, what I mean by that is all those extra electrons that you've picked up can then dump into some other object, like a door handle, a frame of your car, something to that effect. When that happens, you have a big movement of electrons, and that happens as a spark, or basically as a little bit of electricity, which kind of hurts us when we get that to happen. Now, an extreme example of this is lightning. Okay, if we look down here, we'll come back to this in a second. If we look down here, If you're going to get some static electricity to build up, you need 3 million volts for every meter for this to occur. Now, we're looking at, static electricity in our world, right before you touch it, we're looking at micrometers or millimeters of space at the most before this thing is going to jump. Gives us a little bit of a shock, nothing that's going to affect our day. But lightning that lasts a kilometer means it has to have 3 billion volts of electricity running through it to make it happen. Okay, so it's a huge static discharge that happens. And where does it get all those extra electrons? Well, it actually comes from the air sliding past itself, the clouds sliding past themselves, the turbulence in the air alone sliding across our planet themselves in the air generates this scraping effect or this friction. And this friction doesn't make electrons, it starts to gather them in different locations. Okay, so they kind of bundle up. And then at some point they get to be too much and they have to get rid of them. So there's enough there that they discharge. Sometimes they just discharge to another cloud. That's when we have cloud to cloud lightning. That's kind of pretty to watch. Sometimes it discharges to the earth, and that's when we have cloud to earth lightning, and that's the dangerous stuff that we got to be careful about. Now, when that happens, we have this breakdown of air. Okay, this is going to get a little bit above our normal level of what we talk about in here, but it kind of gives you an idea of what's happening. So what happens is with this extra electrons, first thing that happens is along the air molecules next to it, some of those electrons get stripped away. So these neutral air molecules that are in the air, the electrons get stripped away from them. That creates ions in the air, so ionized gases. Ionized gases, another name for that is a plasma. Okay, so we create this very thin plasma field in our air. Okay, through that plasma field, electrons can flow. Okay, so we basically create a bridge between our finger and the door handle, the cloud and the earth, someplace for this plasma field to develop. In the instant of time that develops, all these electrons dump, okay, from your finger into the door handle or from the cloud to the earth. And that big dump of electrons is the static charge or that static electricity that we have. Okay, the easiest way to look at it is for an instant in time, the air becomes a wire for it to travel down because of this plasma field. Right? Now, static electricity does come from friction. We're going to talk about some other charging methods later on in the unit, but we want to focus on for static electricity, it's all about the rubbing and the friction between two different things. Okay. Now, once we have static electricity build up, we actually have two different substances that we want to talk about in terms of conduction. Okay. And we look at this idea of how freely does charge move through things. Okay, we have two different things. We have a conductor. We have conductors and we have insulators. Conductors are things that the charge can move fairly freely through them. Okay, it's not 100% free movement, but they travel fairly easily through them. Okay, your conductors are going to be metals. Okay, all of our metals are relatively good conductors in comparison to insulators. Now, insulators are substances that the charge cannot move, all right? So when you give extra electrons to a conductor, those electrons are able to spread out evenly across that substance, okay? This is not necessarily true if there's a point or an edge. At points or edges, they can build up on those edges or points, but typically speaking, the charges can distribute pretty evenly across the surface of that conductor. An insulator, if you give it extra electrons, they remain static, okay? So imagine if you had like a long rod. On a conductive rod, like let's say aluminum bar of some sort, if you put extra electrons on it, they would land on the bar and they would spread out across the entire bar. For an insulator, you can still put extra electrons on an insulator, like a PVC pipe or a piece of plastic or a piece of wood, something like that. But wherever you place them, they stay there, which means one side can have more electrons and the other side might have less. They don't spread out, okay? So that's your big difference between conductors and insulators. Now, when it comes to semiconductors and superconductors, while they're not the focus of this unit, they're worth mentioning, okay? Semiconductors are those things that we control the conduction by varying different properties of the alloy or of the semiconductor we have or the metalloid that we use, okay? Semiconductors are the backbone of all computer chips. All right, because in computer chips, we need to be able to control the flow of electrons very precisely. Okay, conductors allows too much, insulators doesn't allow enough. So this idea of a semiconductor allows us to vary that rate of flow much better, and then allows us to build a computer chip. Superconductors really aren't that useful yet in our world. What I mean by that is, to get a superconductor, it's one that conducts so well that there's little to no resistance to flow. Okay, so that means the electrons would flow across them with no heat buildup, no loss of energy whatsoever. As a result, they would be amazing. Okay, we could power things so much easier. We could power things so much further away. We wouldn't have to worry about heat buildup. That stuff would be amazing. The problem is, superconductors only work at extremely cold temperatures. We're talking down into the single digits, the tens, maybe up to 100 kelvins at the most. Okay, so superconductors at this time, while we have them, we can make them, we can work with them in an experimental sense. As far as I know, there's nothing really that is being used in production value anyway yet, but maybe someday. Okay. All right, guys, we're going to end the video lesson here. In our next one, we're going to talk about how do you charge objects. Thank you.